Welcome to the deep dive. Today, we are opening up your sources on, well, what feels like a pretty critical challenge facing modern computational science. It's this shift, from software 1.0, the old hard-coded algorithms, towards the more flexible learning-based setups of software 2.0.
Right.
But applying this specifically within engineering, that seems to be where the friction is. Neural networks have done amazing things in language and vision, sure. But physics,
Yeah.
where things like stability, convergence, physical constraints, they're absolutely non-negotiable. It seems we've hit some serious roadblocks there.
Precisely. And we've seen really three major persistent issues cropping up again and again. First, these ML-based partial differential equation solvers, the PDE solvers, they often struggle with the generalization accuracy you need for real-world engineering tolerances.
Okay.
Second, you've got the classic curse of dimensionality, making inverse design problems incredibly difficult, sometimes intractable. And third, the sheer complexity just keeps climbing. Think about advanced simulations like additive manufacturing, needing resolution down below 10 micrometers. It's demanding.
So the mission for us today in this deep dive is to really unpack a proposed solution framework that's laid out here, Engineering Software 2.0. And the core technology, the engine driving this, is something called the Interpolating Neural Network, or INN.
That's the key piece, yeah. The paper positions Engineering Software 2.0 is this end-to-end system. It's designed specifically to unify and hopefully advance the three really essential processes you see all the time in science and engineering problems. That's training models from data, solving complex PDEs, and also calibrating unknown parameters from experiments.
Right, the whole workflow. And the claim here isn't just like a small improvement. It sounds like they're aiming for a pretty radical gain in efficiency and scalability.
That's exactly right. The way the INN is architected, it promises orders of magnitude fewer trainable parameters compared to, well, both traditional multi-layer perceptrons, MLPs, and even compared to physics-informed neural networks, the PINNs, which have gotten a lot of attention. And crucially, it does this while maintaining or even exceeding the model accuracy.
Okay, that's a bold claim. Orders of magnitude fewer parameters. And they apparently waste no time trying to prove the potential here. They demonstrate it by building a surrogate model for laser powder bed fusion heat transfer, L-PBF. And the result they report is achieving sub-10 micrometer resolution over a 10-millimeter path in under 15 minutes on a single GPU.
That's the headline result, yeah.
That really suggests we might need to completely rethink simulation costs and timelines. Okay, let's definitely unpack how this INN manages to achieve this kind of unification, stability, and efficiency.
It really starts by establishing a theoretical common ground, finding where these different approaches overlap. The INN is explicitly designed to treat established numerical methods specifically, a finite element method, FEM, as a kind of structural subset of a deep neural network or a graph neural network.
So treating FEM as part of a DNN or GNN?
Exactly. Look, both FEM and neural networks, at their core, they're trying to do the same thing, find a function that describes some behavior. But INN tries to merge the, let's say, the proven stability of FEM with the generalization power we see in neural networks.
That does sound revolutionary, but the immediate question is, if you're fusing FEM and NNs, aren't you risking inheriting the worst parts of both? Is the setup still incredibly labor-intensive, like traditional FEM meshing can be?
That's the critical question, absolutely. And the architecture tries to address it directly through three core processes. First, you discretize the input domain, but you do it using what they call interpolation nodes.
Yeah.
Not necessarily a full mesh in the traditional sense.
Okay, nodes.
Second, and this is key, you define the message passing operation between those nodes. But it's not just some arbitrary learned weight matrix transformation like in a typical GNN. Instead, the message passing is an explicit interpolation function. Think of it like using basis functions, Lagrange polynomials, maybe splines for the message itself.
Wait, so hold on. Instead of passing just a number or a hidden state tensor between nodes, the network is actually passing a continuous functional definition.
Exactly that. The message is the local function approximation for that region around the node.
Ah, okay.
And then the third step is the optimization. You optimize two things. The actual values at each node, maybe temperature, displacement, whatever you're calculating.
Yeah.
And potentially you can even optimize the physical coordinates, the positions of the nodes themselves, all driven by minimizing some defined loss function.
Right. So discretization with nodes, message passing as functions, and then optimization of values and maybe node positions. Once that optimization is done, how do you get the final output? It's not just a prediction at the nose, right? It needs to be a global function.
Correct. The final interpolated output across the whole domain is generated by effectively a graph-level readout operation. You sum up the product of those optimized nodal values and their corresponding nodal interpolation functions, the ones defined during message passing. Mathematically, the architecture provides a pretty clean expression for this. You can view it essentially as one large tensor contraction operation that reconstructs the function across the entire domain.
Okay, that structure makes sense. This brings us then to the mechanisms that really give the INN its rigor, its trustworthiness. Specifically, how does this message passing really differ from a standard GNN? Because this seems to be where the claims about physical reliability come in.
Right. So a standard GNN's message passing, it typically just returns a hidden state tensor, a vector of numbers for each node. You update the node based on its neighbor states. INN message passing, though, returns that explicit interpolation function for each node, not in QJ as they write it.
The function itself.
Yes. And critically, these functions must satisfy the Kronecker delta property, meaning the function null associated with node Jiao must evaluate to 1 at node G's own location 6 and to evaluate the location of all other specified nodes 6k.
Okay, the Kronecker delta property. For the engineers listening, maybe unpack that a bit. Why is that specific mathematical property so critical for establishing trust and stability, especially when you're trying to solve a PDE?
Because that property, knowledge ASK, allows the INN solver to achieve what's called strong imposition of Dirichlet boundary conditions and initial conditions.
Strong imposition, as opposed to weak.
Exactly. This is fundamental. Many traditional data-driven PDE solvers, like a lot of PNNs, they often only impose these critical physical boundaries weakly. They do it through regularization terms in the loss function.
Which means they can be violated sometimes.
It can lead to boundary violations, yes. The penalty might not be enough, or the network finds a way around it. INN structure, because of that Kronecker delta property, intrinsically respects the physics at the boundaries, right down to the node level. The condition is met exactly at the specified nodes.
That feels like a massive differentiator for reliability in engineering contexts. All right. The paper then goes on to illustrate how this INN framework can actually create a whole spectrum of approximation capabilities. It's not just one fixed method. It goes from highly localized, stable approximations all the way to non-local ones, just by tweaking the message passing steps and the number of hops within this graph structure.
This is the generalization part, yes.
There.
It's quite elegant, actually. If you set the internal parameters, the number of message passing steps, Q and hops, to their minimum, like Q1, S1 hop, the INN mathematically degenerates. It becomes equivalent to the standard linear shape function used in basic finite element method. That's your most localized, very stable approximation.
Okay, so it can reproduce standard FEM.
Yes. But then, if you increase the complexity, say Q2, S2 hops, you start constructing what are called compat-supported functions. These have higher nonlinearity. And interestingly, this configuration becomes equivalent to more advanced numerical methods like the generalized FEM, GFM, or something called CHNN, convolutional hierarchical deep learning neural networks.
So you can dial up the complexity within the same framework. And what happens if you push that connectivity all the way to the maximum hop length?
Then you end up with a non-local approximation. This starts to mimic mesh-free methods like moving least squares or radial basis functions. And these non-local methods are quite interesting because they sometimes exhibit what's called superconvergence, faster convergence than you might expect based on the polynomial order alone.
Wow.
The really elegant part here is that the number of global degrees of freedom, basically, the number of nodes you're solving for, can remain constant. But the computational method itself shifts along this spectrum, from localized FEM-like to non-local mesh-free-like, all within the same INN structure.
That's quite flexible. Okay, we've established how INN builds instability through strong boundary conditions and flexibility through this approximation spectrum. But how does this structure actually scale up? How does it tackle those massive high-dimensional problems we talked about earlier, like that 8-dimensional simulation? That's where the curse of dimensionality usually kills you.
Right.
And the paper proposes leveraging something called tensor decomposition, TD, to handle this.
Yes, this is absolutely the efficiency breakthrough component.
Yep.
When you're solving these high-dimensional problems like the spacetime parameter or STP heat equation they use as an example, if you were to use a regular grid or mesh, the number of trainable parameters or degrees of freedom, it grows exponentially with the dimension. The cost scales like the product of the number of nodes you need along each dimension. J dollars times J2 times dots times JD. That explodes very quickly.
That exponential scaling is precisely why those big engineering simulations have historically taken months or even years, right?
Exactly. It just becomes computationally infeasible. Tensor decomposition. And they mention specific techniques like Tucker decomposition or candy-comparafac, also known as CP decomposition.
Yeah.
These methods solve this scaling problem. They work by effectively replacing that single, huge, high-dimensional interpolation tensor with a series or combination of much smaller one-dimensional interpolations.
Okay, breaking it down dimension by dimension.
Essentially, yes. The upshot is that this converts the scaling growth from that crippling exponential complexity proportional to the product, prod G, to a much more manageable linear complexity. The cost now scales roughly with the sum G hours.
Hold on. Replacing a cost that multiplies across dimensions with a cost that just adds them up, that's not just an efficiency gain. That fundamentally changes the economic viability, the possibility of even attempting certain simulations.
It absolutely does. It enables the computational feasibility of problems that were previously, well, physically impossible to solve on current hardware, or would require completely absurd amounts of storage, like petabytes, just for the setup data. TD is really the key mechanism that unlocks those incredible efficiency numbers they reported in that L-PBF benchmark.
Okay, that connection is clear now. Let's then turn our attention to the empirical evidence they present across those three major applications. The INN as a trainer, a solver, and a calibrator. Starting with the INN trainer, used for surrogate modeling. What did the benchmark show there, comparing it to, say, a standard MLP in terms of training speed and parameter count?
They used a benchmark regression problem, trying to learn a physical function with 10 inputs and 5 outputs. The INN model they constructed was pretty compact, only 8,250 parameters. And it converged to their stopping criteria in just 13 epochs.
Between epochs and the MLP.
Well, they tested various sizes. The largest MLP they used had nearly 3 times the parameters, 21,805, but it required 45 epochs to reach the same level of accuracy.
So, significantly faster convergence with substantially fewer parameters. That seems to confirm the architectural premise about efficiency. And what about in that real-world application, the L-PBF control scenario?
There, the results were even more pronounced. The INN trainer was between 18 and 31 times faster to train than the comparable MLP setup, and it slashed the number of trainable parameters needed by 82%.
Wow, 82% fewer parameters.
Yes. It really validates the advantage of using these compact-supported interpolation functions, which are inherently local compared to the globally approximating nature of standard MLPs like those using sigmoid or ReOU activations. MLPs often need vast parameter counts just to accurately capture sharp local behaviors or high gradients. INN builds that locality in structurally.
Okay, that makes sense. Let's move to the INN solver then. This is where we get into solving those high-dimensional STP PDEs directly, focusing on reliability first, which is paramount for engineering confidence. How did the INN's performance compare to PNN's when it comes to the convergence rate? Does the area decrease predictably as you refine the model?
This is a critical point. They used a simple 1D Poisson's equation as a benchmark here. The INN framework, when it's configured to essentially emulate known numerical methods like FEM or CNN, it shows a proven predictable convergence rate. This means the error they measured, H1 error, its decay, is reliably proportional to the polynomial order P of the approximation. You increase P, the error goes down predictably.
And the PNNs?
Critically, the PNNs they constructed using standard MLPs under the exact same test conditions failed to reveal any consistent convergent behavior. The error didn't reliably decrease with refinement in the same way.
That's concerning for PNs in critical applications.
It is. Predictable convergence is really non-negotiable for engineers. It's what allows them to select a mesh resolution or a polynomial order and have confidence in the resulting accuracy. Without it, you're flying blind to some extent.
Absolutely. Okay, so that covers convergence. Now for the high-stakes benchmark. That 8-dimensional L-PBF space-time parameter heat equation. This is where the true scale of the efficiency gain enabled by TD should really come into focus.
Yeah, this is probably the most defining data point in the paper regarding computational scale. They estimated that using a traditional data-driven approach, specifically a finite difference method, FDM here, for that specific 8D STP problem, it would require something like 2,600 years of computation time.
2,600 years.
And generate over 7.8 times 10 to the 8 gigabytes of storage for the full training data set needed beforehand.
That's nearly an exabyte, 780 petabytes, just for the setup data.
It's a staggering computational expense,
Right.
completely impractical.
Right.
The INN solver, on the other hand, because it leverages the governing equation directly and treats the uncertain parameters as parametric inputs within the solver itself, meaning you don't need that massive offline data generation campaign. It achieved the result, solving that AD problem, in just 15 minutes on a single GPU.
15 minutes versus 2,600 years.
And it achieved exceptional accuracy, too, with a coefficient of determination, r-squared feed, of 0.9969.
So it essentially eliminates that entire upfront data generation bottleneck that plagues many purely data-driven approaches for parametric PDEs.
Precisely. It shifts the paradigm from learn from massive data to solve the equations efficiently across the parameter space.
Okay, that's incredibly compelling for the solver application. Finally, let's look at the INN calibrator. This tackles the inverse problem, trying to figure out unknown parameters like heat source properties based on limited, sparse experimental data. This is a known weak spot for many black box ML systems, right? They need lots of data.
Yes, inverse problems with scarce data are notoriously difficult for purely data-driven models. They can easily overfit or just fail to capture the underlying physics from sparse observations. The INN's advantage here stems from its foundation in interpolation theory and its ability to incorporate physics strongly. The calibrator uses a previously trained or solved INN model, which is already known to be accurate and respect the physics, as its forward model within the inverse optimization loop.
And because the INN is built with these smooth interpolation functions,
it's fully differentiable. That's crucial for using efficient gradient-based optimization methods to find the unknown parameters that best match the sparse experimental data.
So what was the performance contrast they showed compared to using, say, an MLP surrogate model when the data was genuinely scarce?
They tested this using only 28 sets of sparse melt pool temperature measurements from experiments. Very limited data. The parameters calibrated using the INN forward model produced simulation results where the mean melt pool temperature differed by only 7.9% compared to the experimental reference values.
7.9% difference with scarce data. That sounds pretty good.
It is. In contrast, using an MLP surrogate trained on the exact same limited data as the forward model for calibration, that resulted in a mean temperature difference of 44.1%.
Wow, 44% versus 7.9%.
Yeah, a huge difference. It really confirms that the inherent structure of the INN, rooted in numerical methods and interpolation, makes it far more effective at learning and representing the necessary underlying physics, especially when experimental data is hard or expensive to get.
Okay, so pulling all this together, what does this really mean for the future of engineering software? If we summarize INN's core contributions to this idea of engineering software 2.0, we've got a framework that drastically cuts down the parameter space and storage needs, primarily through tensor decomposition.
Right.
It significantly boosts training speed and, importantly, solver reliability through mechanisms like strong boundary condition enforcement. And it successfully tackles these previously intractable high-dimensional space-time parameter problems by integrating the stability of numerical methods directly into the neural architecture.
I think that's a fair summary. The INN architecture seems to successfully leverage decades of established numerical analysis theory, interpolation, FEM concepts, tensor methods to directly address some of the critical failure points we've seen when applying current software 2.0 models, like standard MLPs or even some PNNs, to high-fidelity physical science problems. It really looks like a potentially scalable, reliable, and highly efficient pathway for handling these complex tasks across the board. Training surrogates, solving PDEs directly, and doing inverse calibration.
Which brings us then to a final provocative thought for you, our listener, to consider. This builds on the open research questions mentioned in the paper itself. Because these INNs are constructed using explicit, understandable physical and mathematical concepts, interpolation functions, shape functions, nodal values, things engineers work with. The paper suggests they naturally offer a pathway towards what they call model-based interpretability. You can potentially look inside the trained model and understand how it's representing the physics.
And this raises a really important, maybe fundamental question for the field. Can INNs, or architectures like them, finally bridge this gap? The gap between, on one hand, highly accurate but often completely opaque black box neural networks, and on the other hand, the kind of transparent, stable, verifiable models that engineers absolutely require for high-stakes, safety-critical applications. If INNs can demonstrably maintain that high predictive accuracy, while also offering a structural clarity that developers, domain experts, and even regulators can understand, analyze, and ultimately trust, well, that could fundamentally change how we validate and deploy machine learning and engineering across the globe. It's something to watch.